Hi, Algebra 2. This is a video of the homework answers for Lesson 3, Normal Distribution. So you're going to be using your calculator for all of these problems. I will show you how you can not use your calculator if you want to, but for all of them, we're going to use our calculator. So number 1 has a bunch of different parts, and we're going to use your calculator. You're going to hit that second vars again, which is like right above the tangent button. So first one, A, I want to know what percent of the data is greater than 16. So in this question, I have a mean of 16. The data is normally distributed. So that is important that it says normally distributed. So by that, they mean that it's following this curve right here. This is a normal distribution based on standard deviation. So this is a curve where this is 1 standard deviation away, 2 standard deviation away, and the percentage of that are within 1 or 2 standard deviations away. So I want to know what is greater than 16. 50% of the scores will be greater than 16 because 16 is the mean. So that one I didn't need the calculator for. B, I need my calculator. So I want to know the percentage of scores that fall between 10 and 22. So again, you hit your second vars, you scroll down to number 2, it says normal CDF. Now it depends on what calculator you have. If you have the newer calculator, when you do that, it's going to ask you for the lower and the upper score. So the lower score right here, I want all the scores between 10 and 22. So my lower score is 10. My upper score is 22. This is the list that you're always going to put it in: lower, upper, mean, and then you're going to do the standard deviation. So again, the mean and the standard deviation are right here. It comes from the problem. The only thing that's changing on all of these is the lower and the upper. So if I want the scores between 10 and 22, I do lower is 10, upper is 22, mean is 16, standard deviation is 6, hit enter, and it gives you the percent. Now, if you did not want to do that, notice the scores between 10 and 22. If the mean is 16, 16 minus 6 is 10, and 16 plus 6 is 22. So you're talking about all the scores that are within 1 standard deviation of the mean. And what you can do is you can look at this normal distribution. All the scores that are within 1 standard deviation of the mean is everything from here to here. And you would have to add up all these percents. So if you added up 19.1 plus 15 plus 19.1 plus 15, okay, so everything I'm highlighting right here is within 1 standard deviation of the mean in both directions. And if you were to add up all these percents, then that would also equal the same answer that I had back here, which was my 68.2. Okay, so that's how you do it without using your calculator. I want to know all the scores greater than 28. So again, second vars, normal CDF. My lowest score is 28. Now, if there is no upper score, we just use 1,000. So we use 1,000 for the upper score. If there's no lower score, then I use negative 1,000. It's just easy to put those high numbers in because basically it's going on and on forever and ever. So I actually did 28.1 for my lower, 1,000 for my higher. And again, that 16 and 6, I'm just going to highlight so you see that stays the same the whole time. So all those go into my calculator and I get 2.3%. Less than 1. So my lower is going to be negative 1,000. It's less than 1, so I just did 0.999. And then again, my mean and my standard deviation are 16 and 6. Those are staying the same the whole time. The only thing that's changing is the lower and the upper. And I get 0.6%. Falls between 4 and 19. So my lower is 4, my upper is 19. My mean and my standard deviation are staying the same, 16 and 6. Put that all in my calculator and I get 66.8%. And then all the scores between 22 and 31. So 22 is my lower, 31 is my upper, and 16 and 6 are staying the same. And that gives me 15.2%. All right, number 2 is a multiple choice. The weights of Siamese cats are normally distributed, so it's important that it's saying that. That's the only reason why we're allowed to use our calculator or look at that normal distribution curve. So normally distributed, a mean of 6.4 and a standard deviation of 0.8. Okay, so those are going right here, 6.4 and 0.8. A breeder of Siamese cats has 128 in his care. How many can expect to have weights between 5.2 and 7.6? So 5.2 is my lower, 7.6 is my upper. My mean is 6.4. My standard deviation is 0.8. All that goes into my calculator. I do get 86.6%. Now, that's not the answer. I want to know how many. I don't want the percent. I have 128 cats. So I take that 86.6% and I multiply it by 128, and that gives me 110.89, and that gets rounded to 111 cats. Number 3, I have a quart of apple juice. The weights are normally distributed. I have a mean of 64. I have a standard deviation of 3. So those are going to be right there. What percent of the bottles would have less than 58 ounces? So anything less than 58, I have no lower number. So my lower number is negative 1,000. My upper number is 57.999 because I want to be less than 58 ounces. All of that goes in my calculator. So my lower, my upper, my mean, my standard deviation goes under second VARS normal CDF. And that gives me 0.02273. So that if I move my decimal 2 places is 2.27 or 2.3%. Historically, daily high temperatures in July in Red Hook, New York are normally distributed with a mean of 84 and a standard deviation of 4. How many of the 31 days of July can a person expect to have temperatures above 90? So 90 is my lower number, actually 90.1. My upper number is 1,000. Not that it would get that high, but it goes, there is no ending number. So I'm just going to use 1,000 for that upper number. My mean is 84. My standard deviation is 4. Okay, so the only thing that they're going to give you the mean, they're going to give you the standard deviation. The only thing that you're really that you have to figure out is that lower and that upper. If there is no upper, we use 1,000. If there is no lower, we use negative 1,000. All of these numbers go into my calculator, and it's 0.06362, but I don't want to know the percent. I want to know how many of the 31 days, so I multiply that by 31, and I get 1.97, and that is 2 days, because I'm going to round that off. 5, I have the weights of 4-year-old boys are normally distributed with a mean of 38 and a standard deviation of 4. Perfect. Which of the following weights could represent the 90th percentile of the weight of a 4-year-old? So this one, I can't really use my calculator, but you have to remember in that normal distribution, the 90th percentile is between 1 and 1.5 standard deviations above the mean. Okay, so again, the 90th percentile is between 1 and 1.5 standard deviations above the mean. So if I take the mean and I add 1 standard deviation, I get 42. If I take the mean and I add 1.5 standard deviations, I get 44. Again, the mean is 38, the standard deviation is 4. So 38 plus 4 is 42. The mean is 38. If I add 1.5 standard deviations, I'm going to add 6, and that's 44. So basically, it's the scores between 42 and 44, which is why I picked 43 pounds. Okay, so that one was definitely a little bit harder. Next page, number 6. The lengths of songs on a radio are normally distributed with a mean of 210. If 38.2% of all the songs have lengths between 194 and 226 seconds, then the standard deviation of this distribution is what? 38.2 represents the amount of data that falls within 0.5 standard deviations. What do I mean by that? Here is my mean in the middle. 38.2 would be, let me erase these, within half a standard deviation either way. See this 19.1 and this 19.1? So if I added those up together, that's 38.2. So each of those are within a half a standard deviation above and below the mean. So I'm just taking those. So since 38.2% is the amount of data that's within half a standard deviation of the mean, if I take 210, that is the mean length, and I subtract 194, that's 16. That's a half a standard deviation. Okay, so I'm talking about something with 32 seconds. So 210 minus that 194 is 16, and that is a half a standard deviation. So a full standard deviation is 32 seconds, double that. Heights of professional basketball players are normally distributed with a standard deviation of 5 inches. If only 2.3% of all pro basketball players have heights above 7 feet 5 inches, then which of the following is the mean height of a pro basketball player? So 2.3 is the amount of data greater than 2 standard deviations. So 2.3. So basically, I am talking about, let me highlight that in a different color, this 1.7, 0.5, and 0.1. If you added those all, that's 2.3. So I'm talking about anything greater than 2 standard deviations above the mean. All right, so 2.3 is the amount of data greater than 2 standard deviations above the mean. 7 feet 5 inches is actually 89 inches. I did 7 times 12 plus 5 is 89 inches. If I take 89 and subtract 2 standard deviations, remember a standard deviation is 5 inches. So it's 89 minus 5 is 79 inches. So that would be the mean height. 6 feet 7 inches is the same as 79 inches. All right, on a recent statewide math test, the raw average score was 56 points with a standard deviation of 18. Okay, so this is my mean. My mean right here is 56, and my standard deviation is 18. The scores were normally distributed, and 24,000 students took the test. Answer the following questions. What percent scored below a 38 on the second test? So this is my calculator. Second, VARS, normal, CDF. My lowest score I don't have, so I just did negative 1,000. I probably could have put in 0 right there. Would not change it. Below a 38, so I did 37.99. My mean is 57, and my standard deviation is 18. Okay, all that went into my calculator, and I got 0.15864. So if I move my decimal 2 places, that's 15.9%. Now, if I had 24,000 students take this test, how many students scored less than a 38? So I'm going to take that 15.9%, or I'm actually going to write it as 0.159, and I'm just going to multiply that by the 24,000 students, and that's 3,816 students would have gotten a score less than a 38. If the state would like to scale the test so that 90% would correspond to a raw score that is 1.5 standard deviations above the mean, what raw score is needed for 90%? So I'm going to take this mean, 56, I'm going to add 1.5 standard deviations. So remember, standard deviation is 18, half a standard deviation would be 9. So 56 plus 18 plus 9 is 83. How many of the 24,000 students receive a scaled score greater than a 90%? So 90% corresponds to 1.5 standard deviations. We did that back here. So I'm going to take 4.4, 1.7, 0.5, and 0.1. And I'm going to add those all up. Where are those numbers coming from? Right here. 4.4, 1.7, 0.5, and 0.1. And that all adds up to, because I'm above 1.5 standard deviations, right? This right here, this line is marking off 1.5 standard deviations. So anything above that, 4.4, 1.7, 0.5, and 0.1, that's going to be, those numbers are right here, are all added up. And I'm talking about 6.7% of the people scored greater than 90%. So 0.067 times the 24,000 is 1,608. Okay. State would like no more than 550 of the 24,000 students to fail the exam. What percent of the total does the 550 represent? So I did 550 over the total amount of students, 24,000, and I got 0.0229166. I'm going to move my decimal over 2 places or multiply by 100, either way, and that's 2.29 or 2.3%. What should the Ross passing score be set at so that no more than 550 students fail? 2.3 needs to correspond to 2 standard deviations below the mean. So 56 minus 18 minus 18, because that's a standard deviation. I want to do 2 standard deviations below the mean, so that would have to be a Ross score of 20. Okay?